This is still for chapter 4, section 2. And today we're going to be talking about linear and angular speed. So, obviously, that means there is a difference between the two. There we go. Okay. So we're talking about linear and angular speed. One of the things that we're going to start out with is just kind of doing some unit conversions. So, have you guys ever heard of unit analysis or dimensional analysis is what it's sometimes called? No? Okay. So, we're going to start with unit analysis, which is basically just a systematic method for converting stuff. Okay, so a lot of times it's really easy for us to convert, like if I want to convert from feet to inches. You guys know how to do that, and it's pretty intuitive whether to multiply or divide, right? But as the problems get more complicated, and when we start to get to what we call like derived units, so things that aren't just like a single unit, like if you have feet per second or miles per hour, and you want to convert that, you're actually dealing with two units, and it gets kind of more confusing on what I need to multiply by, what do I need to divide by. Unit analysis is just a systematic way of doing that. Okay, so I'm going to start out with 21.5 inches per second, and I want to convert that to feet per minute. It's actually pretty straightforward once we get the hang of it. So the first thing I want to talk about is these rates. 21 inches per second is the same as like saying, hey, that object is traveling 21.5 inches in 1 second, right? It's really a division problem. So we can write it as such. 21.5 inches. And I'm always, for unit analysis, I'm going to set these up as fractions. 21.5 inches in 1 second. Because again, that's going to be the same rate. Even if I was dealing with different distances, it could be the same as like 43 inches in 2 seconds. But if I divide it, I'm going to get the same rate, right? But now, if I'm trying to convert, I look at the units I'm trying to convert to. And we're going to multiply by a conversion factor, okay? So whatever I multiply by, it has to be equivalent, okay? That's the only like criteria for what we're doing, is it has to be equivalent. And I just basically look at one unit at a time. So if you could do either the inches or the seconds. I'm gonna start with inches, okay? So if I want to go from inches to feet, I just do one unit at a time, okay? Well, you need a conversion factor. So I need two things that are the same.
12 inches.
12 inches is equal to 1 foot, okay? Now, when we set it up, you're going to put another fraction bar. The units that you want to cancel need to be opposites. Okay, because I'm going to cancel the inches out. 12 inches is equal to 1 foot. That's this process of unit analysis, is the units themselves, if they're on opposites, like one's on the numerator, one's on the denominator, they will cancel. You're treating it like a variable. The label feet is going to be left. Does that make sense? So that's a systematic way that will work every time for converting units. So that cancels out the inches and I'm left with feet, but now I have to go from seconds to minutes. So again, you have to have a conversion factor. They have to be equal. So I think, well, 1 minute is equal to 60 seconds, right? I need to cancel out the seconds over 1 minute. So the seconds will cancel.
We did this.
Yeah, I'm guessing you guys are somewhat familiar with this.
It was called unit analysis, we just did it.
Okay. Yeah, it's technically called unit analysis. You can treat the labels like variables or algebraic quantities that will cancel out. The two things you have to keep in mind, whatever you multiply by, these always have to be equivalent, okay? 1 foot is the same as 12 inches. 60 seconds is the same as a minute. And then you just have to figure out which one goes on the numerator and which one on the denominator to cancel out what you want. I want the inches to cancel. So now, all that I'm left with is feet per minute, which is what I want. So then I just multiply it all together. So it's 21.5 times 60. And then I take that answer divided by 12. And actually multiplication, division, the order doesn't really matter, so you can get creative. You could do 60 divided by 12 is 5. And then, anyway, that's it. Beside the point, because we should end up with 107.5 feet per minute.
Can we just have a lesson about doing this because I'm horrible at this?
So what happened to
So, example 2. We're going to convert from 30 miles per hour. And this may not be how you guys are used to writing miles per hour because you usually see it on vehicles as mph. But I want you to do it the same way because we're actually comparing two quantities, right? Miles per hour. And we're going to convert this to inches per second. Because again, I need to be able to set this up as a fraction in order to use unit analysis. And so again, I take this rate and I set it up as a fraction. It's 30 miles in 1 hour. And again, that's just like the unit rate. It'd be the same as if I took 60 miles divided by 2 hours or 90 miles divided by 3 hours. I get the same rate. So you guys kind of walk me through this one. I've got to multiply by a conversion factor. Let's deal with the miles first, okay? You may not go, you can if you want, but you don't have to go straight from miles to inches. Do we know how many feet are in a mile? 5,280. If you don't know that, that's a good fact you need to memorize, not just for school, but for life in general.
I learned that from Carter.
5 tomatoes, best way to remember that.
What?
5
tomatoes.
5280. 5 tomato.
Okay. That's more confusing than just 5,280.
5
It's
tomato.
easier to say.
All right. So you can do it in one step if you want. I'm going to show it in two. Okay. I want to go from I want to go from miles to feet. So what's my conversion factor there? 5,280 feet is 1 mile. Okay. And I know which one needs to go on the denominator.
Could you go by miles? Could you go straight to inches?
Yeah, if you know how. So if you want to, that's fine. I'm still going to show it in 2 steps, but
Going all or nothing.
so 5,280 feet is 1 mile. I put the miles on the denominator because I want those to cancel. And I like to cancel stuff as I go. It helps me keep track of where I'm at. Okay? So now I'm in feet, but I want inches. So what's my conversion factor from feet to inches?
12 inches and a foot.
12 inches is 1 foot. Which one needs to go where?
The feet need on the bottom.
Yep, I put 1 foot on the denominator so that I can cancel the feet out. So now I'm 2 inches. Now I want to go from hours to seconds. I'll do this one in 1 step. Again, if you don't know how many seconds are in 1 hour, you could do it in 2
60
steps.
times 60.
We know, hopefully, it's pretty intuitive to think that I just have to do 60 times 60, right? Which is 3,600. So 1 hour, which I put it on top to cancel, is 3,600 seconds. Okay. And then we just multiply straight across.
Equation, do it.
Now, I'm going to show you guys how to convert using angular units, because that is something we're going to have to do for this section. So instead of dealing with like distances, we're going to have 8.7 revolutions per minute.
RPM.
And I want to convert that to radians per second. So yeah, RPMs, you guys will see on tax on cars, vehicles, equipment, revolutions per minute. We want to write it like this so that we can use unit analysis. So this is 8.7 revolutions in 1 minute. Is kind of what that means. So 8.7 revolutions over 1 minute.
Let's do the seconds first.
The minutes you mean? Or minutes to seconds? Okay, that's fine. 1 minute is 60 seconds. So I put 1 minute. Okay. Now, I have to go from revolutions to radians, so I have to have a conversion factor that's the same.
Is it
1 revolution equals 2 pi.
It's what?
360?
Well, 360 would be degrees though.
Okay.
Good, I typically have that come up. Yeah, 1 revolution is 360 degrees, but how many radians is that? 2 pi, right? There's 2 pi radians in a full revolution. Okay? So-
we just put 2 pi or 2 pi radians?
Either or, I don't always label radians. If you want to, if that helps you stay organized, that's perfectly fine.
So revolution-
Typically, when we see that, we know that that's radians. But if you want to label 2 pi radians, that's fine.
17.45 over 60.
Okay, but then we need to divide that.
0.911.
It's just, you just keep putting that together.
0.911.
No, we're not quite done yet. I'm gonna do one where we convert kind of the other way. I'm gonna start with radians. So we're gonna have 4 pi over 3 radians per second. I want to go to revolutions per minute.
Will we just write the fraction like that then?
Well, sort of. So, see what I want to do here. Typically, you want to avoid writing a fraction inside of a fraction. That just gets messy and more complicated than needed. Okay. So does it make sense that, I mean, I could do 4 pi over 3 radians in 1 second, but doesn't that make sense that it would be the same as 4 pi radians divided by 3 seconds?
Yeah, so that's perfect.
It'll be the same unit rate. Does that make sense?
If you divide it by 1, it's going to be the same thing.
Right. So I just need to convert this to revolutions per minute. Which one do you want to convert first, the radians or the seconds? Radians to revolutions, okay. What's my conversion factor?
2 pi over 1.
2 pi radians is 1 revolution.
So this is where we're doing, I'm not understanding the point. Do we ever have to divide the fraction?
And then I want to go from seconds to minutes. So
So what equals
1 minute is 60 seconds. Those will cancel. And
4 times 60.
So the pi's cancel out, and that is going to be
240 divided by
40,
Okay, you go,
right?
yeah.
So that is it for the unit conversion part. Now we're going to go into, well, what the title of the section actually was. We're going to be dealing with linear speed and angular speed and how those two things are related, because there is a relationship there. So first we've got to define a few things. So linear speed,
Do we have to write our L that fancy?
no. So linear speed is just how far an object moves in a given amount of time. And I'm going to underline far. And for this whole section, we are going to have some different variables because we're going to have a few formulas. And so for linear speed, the variable that we're going to use for that is just a v, like for velocity. Technically, speed and velocity are not exactly the same thing, but for right now, they're close enough to use them interchangeably. I do want to talk about some of the units for linear speed, because again, with linear speed, we're talking about how far an object moves in a given amount of time. That's why we have things like, when we say 60 miles per hour, that means an object traveling at that rate would cover 60 miles in 1 hour, right? So we're talking about how far. All units of linear speed are going to be some type of distance divided by some type of time. So examples of the units that you would see for that could be things like miles per hour. But there's lots of other units that we could have. What would be some other examples?
Feet per second.
Feet per second. What else?
Inches per minute?
Inches per minute. That'd be something moving real slow. Right, well, depending on how many inches. But if you said like
Different
5
combination.
inches per minute,
I was just trying to make a
pretty
different
slow.
combination.
But yeah, that work. It's still a distance divided by a time, so perfectly acceptable.
So can we just write distance divided by time for this?
I'll just hold on 1 minute. Okay.
I-
Yeah, technically speaking,
One winner.
any unit of distance divided by any unit of time would work here. You could have centimeters per hour would be a linear speed. It'd just be kind of ridiculous, but it would still be acceptable, right? Same type of thing. So now, I am going to write a formula for linear speed. And that is that our speed is distance divided by time. Now that doesn't show up very well. Change colors. Okay, that makes sense, right? If I travel, let's say 30 miles in 5 hours, then that would be an average speed of 6 miles per hour, right? Okay. Now, what we're going to talk about now is for a circular path. Because we're going to be dealing with rotational motion. We're still going to be dealing with linear speed, so think about things like miles per hour, feet per second, but of an object that's on some type of rotating device. So imagine like the speed of a person on like a carousel or a, some type of like amusement park ride. I don't know, something like that. When they're going around a circular path, the distance just is going to get replaced with the arc length that we're traveling. So it's still going to be V, but it's going to be S over T. And this is the formula that we're going to be using the most. So I am going to circle that one. Even though typically you can think of it as distance divided by time, just for what we're doing, the distance traveled is going to be arc length.
So S equals the arc length.
Yes.
Or theta times your.
So if you want, you can label. It's still going to be measured in units of distance. So it's still going to be, that arc length will be like 12 feet or 15 meters or something like that.
So equal radius times.
Yep. So now I want to move on to angular speed. Okay. So angular speed is the change in angle of rotation any given amount of time. Very similar to linear speed, but there's some important differences. Okay, so I'm going to go through kind of the same sort of thing as we did up here with linear speed. First off, we have a different variable that represents angular speed. We're going to have different units and a different formula. The variable that we use for angular speed is actually the Greek letter omega. It looks kind of like a W. Hmm? You guys know, like, you've heard like alpha and omega getting in. So this is actually the last letter of the Greek alphabet.
Which one's the one
W?
that does the like food?
I don't know.
Can we just use an ohm symbol?
W is the last letter.
It's not W, it's omega.
Well, it looks like a W.
Well, use your imagination.
That's a curvy W.
It's correct. There you go.
They just opened it.
All right, so it's the change in angle of rotation. So I want you to think from angular speed, it's not going to be a distance divided by time. We're not worried about distance, we're worried about an angle. Okay?
Degree.
So it's going to be things like, you could use degrees, although we typically don't.
Radians.
Theta.
It's going to be units like radians per second, or a pretty common one that we use here in the US with the good old imperial system, revolutions per minute. That would be like RPMs on your tach. Or you could have revolutions per second, radians per minute, any kind of different combination. But typically your angle is going to be in radians or revolutions, and then divided by a time interval in minutes or seconds. Although you could certainly use hours or any other time unit. It's going to be an angle divided by a time, which should make sense when we get to our formula, because the formula for angular speed,
Is omega.
omega, is equal to theta, the change, the angle of rotation, divided by time. Now, just to kind of clarify something here, for this formula, it doesn't matter what theta is, just like here it doesn't matter what units of distance is, it just is going to affect the units of your answer. So for example, if I put in 10 revolutions divided by 2 seconds, that'd be 5 revolutions per second, right? if I put in radians, then it's radians per second, right? The units here just are going to be the units of your answer here. Okay. Now for some stuff we're going to look at later, that'll be a little bit different story. All right, so now we're going to look at how are the two things related. How are they related? Okay, so I'm talking about how is angular velocity related to linear velocity. Okay,
You need speed.
so yeah, speed. So I like to kind of have a practical comparison. One's got a radius of 5 feet, one's got a radius of 10 feet. So let's pretend these are two merry-go-rounds, right? Like what you used to have at the playground at elementary school. Yeah, a small merry-go-round and a big merry-go-round. Just for the sake of discussion, let's say that they have the exact same angular speed. Okay? Let's say, what do you think is an appropriate angular speed for a merry-go-round? How many revolutions should it make in 1 minute?
35.
35.
That's a lot.
I don't think it's that many, honestly. We got them babies spinning.
Okay. But for the sake of argument, let's say that they're both making the same amount of revolutions in 1 minute. Okay? So this merry-go-round is making 35 complete revolutions in 1 minute, and this one is also making 35 complete revolutions in 1 minute.
Those are some pretty.
How are the linear velocities going to compare between the two? Are they going to be the same because angular speed is
No.
the same?
No.
Are they going to be different? If so, how can we know? What do we think? What?
It's because of the arc length. The arc length is going to be different for both of them because you have to find the arc length and it involves the radius. And they
Bingo.
have different radiuses.
Okay, so they have different radii, technically. Think about it this way. Even though they're making a full revolution in the same amount of time, a person, if we've got a little 8-year-old elementary student out here, yeah, I won't worry about names. This guy over here, or gal, is going to make a complete revolution in the same amount of time as this one over here, but this one is going to cover a lot further distance, right? Okay. So which one is going to have the greater linear velocity?
The little one.
Yeah.
The big one.
The big one.
10 foot.
This one's going to go further in the same amount of time, right? Okay. The one with the bigger radius is going to have a greater velocity if the angular velocity is the same. But let's look at how, like, algebraically, how is linear speed related to angular speed? And it is going to involve the radius. Okay? So it's pretty simple, actually. Let's start with our formula for linear speed is arc length divided by time. Okay. But if I break arc length down, well, we don't necessarily have to have a full revolution. So arc length is just, I'm going to do a substitution. Arc length is just r theta, right? Okay. Well, theta divided by time is just omega. So I can replace that with, so linear speed equals the radius times omega.
you lost
So
me
if I-
after the first one.
Okay. Don't necessarily have to follow the derivation as
No.
long as we know this. This is linear speed equals the radius times angular speed. Which makes sense. So actually, if I go back up to my merry-go-round example, I could calculate the linear speed here,
Yeah.
35 times 5, and I could calculate it over here, 35
I'm saying.
times 10.
350 and 175.
So it makes sense. So these are what we call, this is a direct relationship. So if I have the same angular speed, if I double the radius, I double the linear speed. Has some important applications. All right, that's going to be it for notes today.
You are a genius.